In this video, we will use Stokes Theorem to evaluate a line integral. So we're given the line integral of this vector field f over the curve C, which we're told is the boundary of the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we have this triangle, and we're told it's oriented counterclockwise if we look at it from above like this. So let's remember what Stokes Theorem says. It says that our line integral of our vector field is also equal to a certain surface integral of not f, but the curl of f. And here S is any surface whose boundary is the original curve C. So in our case, we can use for S this filled-in triangle. So our surface S will be a part of the plane x plus y plus z equals 1. Or if we solve for z, z equals 1 minus x minus y. Since this triangle lies in that plane. Okay. So, it says use Stokes Theorem. So instead of computing the line integral we're given, we will instead compute this surface integral. So we need to do some setup before we can do this integral. We need a couple things. Well, one, we've already written the surface. It's a piece of this plane, and it's given as a graph, the way that we've written it here. We still need to write what is ds, and we still need to find the curl of f. So let's do those two things. So ds, if you remember for a graph, ds is minus fx minus fy 1. Or it's negative, possibly. You might need to use this instead. But here, the curve was oriented counterclockwise, meaning if we're looking at it so that it's counterclockwise, the normal vector should be pointing at our face. So the normal vector we want to have positive z component, so we do indeed want this version. And by f, so when I say f here, when we're taking partial derivatives, I of course mean this f, for which our surface is the graph. So fx and fy in this case are both negative 1. I forgot the differential. I should technically put dx dy after it. So we just get 1, 1, 1. Okay. Now, we still need to compute the curl of f before we can do this integral. So we'll use our 3×3 determinant, put the partial derivatives here, and put f as the bottom row. Okay, so for the x component, the y derivative of x squared is 0, minus the z derivative of xz, which is x. For the y component, we do the z derivative of y, which is 0, minus the x derivative of x squared, which is 2x. And for the z component, we do the x derivative of xz, which is z, minus the y derivative of y, which is 1. So we have negative x, negative 2x, and z minus 1. Okay. So now we can compute this surface integral. So since we're thinking of the surface as a graph, we want to do this over the region D, which is the shadow of our graph in the xy plane. And here, that's just going to be this triangle. Which goes a distance 1 in the x and y direction. And our curl, we have minus x, minus 2x, and everywhere we see z, we should substitute the equation for our graph. So instead of z, we should plug in 1 minus x minus y. So we have z minus 1, so that's just negative x minus y. Dot. And above, we have ds is 1, 1, 1. Now the region D, we can describe as x goes from 0 to 1, and y goes from 0 to 1 minus x. And if we do this dot product, we get minus x, minus 2x, minus x, minus y. So all in all, we have minus 4x minus y dy dx. And let's pull the minus sign out. And now if we do the y integral first, x is just a constant, so we multiply it by 1 minus x, and the integral of y is 1/2 y squared. And we evaluate from 0 to 1 minus x. Now if we go ahead and multiply all this out and distribute that minus sign through, we end up with 7/2 x squared minus 3x minus 1/2. So the integral of x squared from 0 to 1 is 1/3. So this gives 7/6. The integral of x from 0 to 1 is 1/2. So minus 3/2. And the integral of 1/2 from 0 to 1 is just 1/2. And if we add these fractions together, we will end up getting minus 5/6.